Okay, so before the midterm exam, we started talking about page replacement algorithms, and we said that pages, when the reason why, one of the main reasons why we are using paging is to facilitate the swapping between the disk and the main memory. Instead of swapping the whole programs, why don't we swap the programs page by page? That would be more effective, that would be more efficient. And these are the page replacement algorithms. These algorithms will decide on which page to replace. In my main memory, if there are no enough pages to meet the demands of the current running program, then I have to replace some of them. I have to write some pages to the disk and load some pages from the disk maybe. So these algorithms will make that decision, and these are basically, I am planning to finish up all of those today. These are basically the algorithms that we are going to cover. And I think I looked at the first two of them maybe, yeah. So we said that whatever the paging algorithm is, it must be efficient. Why it has to be efficient? It has to be efficient because, of course, we like everything to be efficient, but this is critical because page replacement happens between the times when you are accessing the memory. If the memory you're trying to access is not on the main memory, then it has to be loaded from the disk, and you have to make that decision very, very fast. Otherwise, your effective memory access time will get even slower. So it must be efficient, and it must be, well, I mean, I can make something very efficient by choosing the first random one. That doesn't mean that it's an efficient in an effective manner. So your answer must be correct too. What is the correct answer? As we said last time, it should be close to its result should be close to the optimal algorithm. Okay, and as you know, optimal algorithm is not implementable. It needs to see the future. So how do we know what kind of decision optimal algorithm will make? We will run our program on a simulator, and after everything happens, we say that if I had the optimal algorithm would have done this way, that way, or this way. Okay, so that's why we say that my result, page replacement result, should approximate the correct answer, and it must be implementable on a real hardware. What does that mean? It means this. Okay, everybody has CPU, everybody has memory. That's why we call those computers, right? But some page replacement algorithm, they ask you to have certain hardware features. They say that I need a hardware that counts the memory accesses for each page, etc. So if you have these kind of requirements, they should be realistic, and it must be implementable on real hardware. And usually we say that it must work well on multitasking systems. Never forget that we are on a multitask operating system. There will be more than one process. We are not talking about a single process only. We are talking about multiple processes, and we should be careful about those. Those are the constraints. Within these constraints, considering all of these constraints, we are going to implement our page replacement algorithms, and these are the tools that the operating system offers us at our disposal. Operating system says that, okay, and with the help of the hardware, of course, for each page, remember this is the case, this is my virtual address space. Virtual address space is divided into virtual pages, of course. This is virtual address space, and this is my physical address space. And this is again divided into pages. Okay, and with the virtual address space, I have the page table, of course. Let's assume that this will be a page table, and in my page table there are referenced and modified bit fields. Okay, this one might say that, okay, this page lives at the physical address frame, okay, page frame, and this one lives here. Also, I should say this page is modified. Sorry, this page is referenced, but it is not modified. This page is not referenced or modified. This page is both referenced and modified. Okay, so I have these R and M bits available for us. So reference bit and modified bit, I'm going to use them. The meaning is that you don't wanna replace a recently modified or recently accessed page because somebody's using it. That page is busy. If you like to replace a page among these three pages, I would choose this one because recently nobody modified it and recently nobody used it, nobody referenced it. Okay, so that's one thing, reference bit and modified bit. Clock interrupts we are going to use a lot. We are going to say that, okay, at every clock interrupt, remember, clock interrupt happens 30 times a second, 50 times a second, depending on your system parameters. We are going to say that every time the clock interrupt happens, I am going to scan all of my page table and see who is busy and who is not, etc. Okay, so I will do that. So clock interrupts are important, and we do lots of useful work when the clock interrupts happens. Okay, I mean, we don't use the clock interrupts only for preemption, only for switching from one process to another process. The other one is page fault interrupts. Who produces the page faults? Of course, the memory management unit. Okay, when I say give me this page, sorry, I never say give me this page. As a program, I say that I like to access this memory location, and the memory management unit say that the memory location that you are trying to access is in a page, and that page is not in the memory. Okay, so it causes a trap. Okay, it causes an interrupt. Of course, who is going to handle the interrupt? Operating system. Operating system comes in and says that, okay, there is a page fault, and I'm going to handle this. And those page fault interrupts will be our tools too, okay, because they will tell us many things about how many times page faults are happening with our system and who is causing those interrupts, and etc. So they are very useful for collecting statistics about our paging system. Okay, and we talked about advice from application. We will come to that later. Optimal algorithm, as we said before, okay, it is simple but impossible to implement because it says that suppose I know the future, okay, if I know the future, then I would know which page, okay. So this is the main thing. If I know somehow the page that will not be referenced longest, that's what we are after, okay. The page that will not be referenced longest. Okay, if I know this somehow, then I am done with the page replacement algorithms, but I don't know. Okay, so I am trying to guess this page that will not be referenced longest by looking at the past. Sometimes I say that maybe I should look at the page that was not referenced longest. Okay, maybe I should look at the page such and such, who is loaded the earliest, etc. So I will try to make these kind of approximations, and I will hope that my result will be very similar to the page that will not be referenced longest. Again, it's not implementable. I need to be seeing the future. So however I'm going to know what kind of optimal results I am going to, the optimal algorithm will say, I am going to run my program first on a simulator, and I will see which pages are referenced in the future, and I will come back to that at the beginning of the program, and at the beginning of the program I will say that, okay, these pages will be referenced at this point and this point and this point and this point, so I can know which page will not be referenced the longest. Okay. Optimal algorithm, yeah, this is not again implementable on hardware, on software, but it's a good. You cannot do better than optimal algorithm. That's why we have this. Okay. I mean, remember what we said about. Remember what we said about your results should be approximate to the correct answer. It is good for us to know the correct answer. Okay. So during the runtime, we will never know the optimal algorithm's result. Okay, let's look at the first one. Not recently used algorithm. Not recently used algorithm does this actually. Okay. At process start time, whatever I am loading, okay, I am loading everything, all the pages with R and M bits 0. That's expected because I did not access them yet. I did not modify them yet, okay, at the process start time, okay. And the second thing is important, on clock interrupts, I clear the Arbits, okay. I clear the Arbits one by one. What does that mean? Every 30 times a second, whenever the clock interrupt happens, I go ahead and I make all of these Arbits 0, saying that, well, you may have been referenced before, but for the next clock interrupt time, I am going to clear this bit so that whoever looks at you, they will think that you were never referenced. So if a page is referenced in the last clock interrupt time, then I'm going to let it stay. Otherwise, I'm going to clear all those referenced bits. And then after I'm going to do this, and after I'm going to do this, I will assign a class label for each page. I will say that if your R bit is 0 and M bit is 0, you are not referenced or modified. Your class is 0. If you are not referenced but modified, you are 1. If you are referenced but modified, you are 2. And if your class is 3, referenced and modified, then your class is 3. Okay, that's what's going to happen. And on page fault, I will discard a random page from the lowest class. So first I am going to replace these, then I'm going to replace these, and then these. Okay, so it looks like I am making my decision based on this only R and M bits. That's why they say that not recently used. Let's look at this name actually. What does that mean, not recently used? I think this is the one that is not recently used. Most not recently used. Why? Because for the last 30 milliseconds, right? For the last 30 milliseconds, nobody has modified this page nobody has modified this page, and nobody has referenced this page. So it is not recently used page. Okay? It is not recently used page. It is not a page that will not be referenced the longest, because I am not seeing into the future, right? I am just looking at the time between the last clock interrupt and this reference. I am saying that, okay, I am saying that this page is not recently used. That's the thing. So I am assuming that the measure of not recently being used is the same as the page that will not be referenced longest. That's my assumption. And how do I know that this assumption holds? Of course, I am going to run simulations. Okay? You are going to write an operating system, okay, on a simulated hardware, and run your programs. See if not recently used algorithm is doing as well as the optimal algorithm. So how do I compare the performances? Okay, comparing the performances is this way. How many page replacements does the NRU cause, and how many page replacement does the optimal algorithm cause, right? You just compare it. If the optimal algorithm causes 50 page replacements, then you cannot do better than 50. and if the not recently used is causing 100 page replacements, you are saying that there is a difference between difference of 50 page replacements. You are doing extra 50 page replacement, and that's not good. Okay, so you are doing the twice the page replacement value of the optimal. So that's how the not recently used works. Okay, by the way, this classification, once it is done, we don't use these classes unless a page fault happens. When the page fault happens, okay, if there is a free page, then I would immediately use it. Okay, just load it to the free page. If there is no free page, all the pages are occupied, then I have to choose one page to replace it. Okay, first you say that if there are a page that that is not referenced or modified in the recent time, then I will replace it. Otherwise, if there is a page that is not referenced but modified, and then I'm going to replace it. Otherwise, if there is a page, I mean, if I don't have anything from class 0, from class 1, class 2, etc., it goes that way. Question for you: why do you think that I replace class 1 pages earlier than class 2 pages? I mean, I understand why I am giving this. I mean, I am saying that I don't like you because nobody referenced you, nobody modified you. Okay, so that's a good indication that nobody is going to reference you or modified you. Okay, that's the reason. But why did they make this order? I mean, why class 1 is before the class 2? Why am I replacing 0 ones before 1 0? I understand this one too, because a page is both referenced and modified. That page is a very, very busy page, so I should keep it. Okay, this is the most available, the most available page. Nobody is using it. This one is heavily modified and referenced. But how about this order? Yes?
Class 2 is going to be transitioned to class 0 when the clock interrupt happens.
Say it louder, everybody can hear you.
Class 2 is going to be transitioned to class 0 when the clock interrupt happens. So the Arbit is going to be cleared. That's why it is more common to get the class 0, right?
Yeah, well, exactly. The idea is this: if this is one, that means what? This happened during the last clock tick time. Okay, remember, interrupts happen every 50 milliseconds. After every 50 milliseconds. Okay, at every 50 milliseconds, I am clearing my Arbits. If this is one, that means that somebody has modified or somebody has accessed this page in last 50 milliseconds, but nobody has accessed this page. Well, I mean, you might say that, how about this one? This one might be because in the last 50 milliseconds, or maybe 100, maybe 150, maybe 200, because nobody clears the embed. Okay, nobody clears the embed. But I know that Arbit is cleared at every clock interrupt. Okay, that's why we replace class 1 before class 2. Okay, so that's not recently used algorithm. Very simple algorithm. And given our tools, remember our tools at our disposal. Reference bit, we use it. Modified bit, we use it. Clock interrupts, we use that too, right? At every clock interrupt, we cleared all the Arbits. Okay, and of course the page fault interrupts. When the page fault happens, we do the classification and do the replacement. So we kind of use almost all the tools that the operating system and the hardware offers us, and that's how we do the not recently used algorithm. The name not recently used means that, okay, this is the one that is not recently used, and this is the most likely one that will be used in the future. Okay, so this is our approximation to the optimal algorithm. The page that will not be referenced longest. Okay, so not recent use algorithm works this way, and resetting M and Arbits. Why do we reset R on clock interrupts, and why we are not resetting M? Why are we making all those R's 0 and M's not 0? Okay. I mean, if I don't reset anything, soon these all will be ones, right? Everybody will be referenced and everybody will be modified. So there will be no difference between them. Okay. By resetting the Arbits every clock interrupt, okay, I know that who was accessed in the last 50 milliseconds between the two clock interrupts. That's why we reset the Arbit on clock interrupts. I can't do the same thing with the M, because you are not free to replace the M, reset the M bit as you wish, because M means that it is modified. If you are replacing that page, okay, you have to write it back to the disk. That page is modified, right? For the Arbit, I don't say the same thing. If the Arbit is reset, to replace that page, I don't have to do anything. I just discard that page. Okay, so M bit is not resettable. Okay, to reset an M bit, tell me, how do you reset an M bit? I like to reset an M bit in a correct way. Yes?
When I wrote this, I can reset.
Yeah. Well, if you like to reset the M bit, you have to write that page to the disk, right? Which will be very, very, very, very expensive. Okay, because you are going to I am trying to save time for my memory access, but now I am writing the whole page to the disk. And the thing is that if I am going to modify that disk location, if I'm going to modify that location again, and I'm going to load it back, and no, that's not a good thing. So we don't reset the M bits. Okay, M cannot be reset until the page has been written out to the disk. Okay, so properties of NRU. Okay, nobody uses NRU, but it's a good introductory algorithm for you to see what's happening. It biases towards discarding unmodified pages. So why? Because when you make those Arbits always 0, 0, 0, okay, your unmodified pages will end up. Your R pages will be in class 0, because I keep resetting them all the time. So it biases towards discarding unmodified pages, but of course it is better to discard the modified page than loading it back again. It's a simple algorithm. Okay, may give adequate performance, adequate performance on some systems. Okay, so that's our first algorithm for replacing pages. Any questions? Some people say that, well, I mean, this is too complicated. Why are we doing this? Why don't we keep a FIFO? Okay. Why don't we keep a FIFO to keep our pages in an ordered list like that? First in, first out. Okay. So whoever is loaded from the desk, it will be my oldest page, then the next one, then the next one. If I need to replace something, just replace the oldest one. Okay, that's the first in, first out thing. But before that, I think I forgot a slide in here, right? Yeah. Before going to the FIFO, okay, let's look at the properties about NRU. It has the essential properties of any page replacement algorithm. It is using our operating system hardware tools, and it is trying to be similar to the optimal. It looks relatively an idle page. Okay, it handles the modified pages, but if a page is modified, then this algorithm tries to keep it all the time. Okay, so to write a modified page back to the disk, what is the condition? Okay, tell me about this. What is the condition for NRU to write a modified, or maybe better that way? What is the condition for NRU to replace a modified page? Under what conditions I am replacing a modified page?
There are no plus 0 pages, maybe?
There are no reference pages, right? If there are no reference pages, only then I can replace a modified page. So it is clearly very biased against keeping the modified pages, even if that page is not referenced at all, right? Even if that page is not modified again. Let's say I have a page that I have modified only once in the runtime of the whole application. As long as there are reference pages, right? Okay, as long as there are reference pages, then I will make them zeros and I will replace them. So it is biased against using them, but it is reasonably efficient. Okay, let's go back to the first in, first out. Okay, this one says that forget about R and embeds. Don't use them. When a page frame is needed, discard the oldest page. How do I know which one is oldest? I will keep them in a linked list. Okay, I will keep them in a linked list. Remember, this is my page table. This is my physical pages, okay, and I have links like these, and these are pages one by one. I have these links. This one says that keep a linked list that says that, okay, this is my start node. After that, this will come. After that, this will come. Then this, then that. So it's basically a linked list. So whenever I get a new page, I will put it at the beginning of the linked list, Fifo. Okay, so I keep doing this, and whenever I need to replace a page, I choose the oldest one. So I am adding new stuff. I am adding new stuff to my page table, or I am keeping this information separate from the page table, but it refers to the page table. Okay, it refers to the page table. So I keep it as a Fifo, and most recently used pages here. This is the oldest page. Whenever I need the page replacement, this one will be replaced. This is as simple as this. Doesn't use R and M. So what is the problem with this? Very simple. We like it. I don't even need the R and embeds. If my page table, if my MMU is so primitive, it doesn't offer me any R and M bits. It is so primitive. Then this is implementable. This is nice, but there is a problem with this one. Can you tell me what the problem is? Replacing the oldest pages is not a good idea all the time. Yes?
Oldest one, maybe most important one, and keep it busy for all time. We need to,
you are saying that the oldest page doesn't mean that it is not busy, right? I mean, this is the oldest page, but I keep using it. Oldest doesn't mean that I am not using it, okay? Oldest doesn't mean that I am not going to access it for a long time. Remember the definition for the optimal algorithm? The algorithm that it says that the page that will not be referenced for the longest, okay, that will be my algorithm. And this Fifo is doing that. I mean, the Fifo says that the oldest one is the same as the page that will not be referenced long. No, that's not a good idea. That's why nobody uses Fifo like this. But the idea that it is so simple is something nice, and we are going to use this idea with a modified Fifo. Okay, it's called second chance Fifo. It's the same as Fifo, but now I will start using the Arbit. Okay, the Arbit I check whenever the page replacement time comes. Let's say I am going to replace a page. This is the oldest one. I don't replace this automatically. I check the Arbit. If Arbit is not 0, okay, I say that, okay, somebody's using this. Somebody's using this. I am not going to replace this page. I will first reset the Arbit, make it 0. I will move this page to the beginning of the list, not at the end, but the beginning. Okay, and I will look at the next one. So basically, this is what I'm going to do. This is the oldest one. If Arbit is 1, okay, then make this Arbit 0 and put this A here, or maybe, okay, A will be here. Now its Arbit is 0, and let's check this B. If B is oldest in this case, let's check if its Arbit is 0. If the Arbit is 0, then I will replace this one. So we are kind of giving the page a second chance to get to the beginning of this list. And if the next time I see this A, if Arbit is again 0, then I will replace it. If Arbit is 1, of course I am going to keep it. Okay, that's the idea. If R is set on an old page, clear the Arbit, move it to the just loaded end of the queue, and approximate behavior LRU somehow least recently used behavior. Okay, so it kind of says again, it's least recently used. If the Arbit is 1 for a page to be replaced, then I know that somebody is using it, so it is recently used. If Arbit is not 1, then that means that nobody is used recently, so maybe I should replace it. It is old enough and I should replace it. Question for you: do I clear the Arbits every time the clock interrupt happens in this case?
No.
No, definitely not, right? I am not clearing the Arbits every time the clock interrupts happens, because if I do that, that's not meaningless. Most of these would turn out to be, okay, would turn out to have Arbits is 0 at the end. So that's not a good idea. Arbit is cleared when the page is at the end, and I am just checking, should I replace this? If no, I am not going to replace it because Arbit is 1, then that's it. And this one doesn't look at the M bit at all, the second chance Fifo. Arbit is good enough for me. Yeah.
What if all the pages are referenced in that case?
Yeah, that's the question. What happens if all the bits are 1? 1, 1, 1, 1, 1, 1, 1, 1.
We are resetting when we put into.
Yeah. So if this one will go to the beginning of the link list, this one will go to the beginning, this one. Eventually you are going to hit this A, and you are going to replace it. Okay, so this one turns into the second chance Fifo. If I do that, if all the Arbits are 1, the second chance Fifo turns into Fifo, right? Because I gave everybody a second chance. Nobody use their second chances, cannot use them, and this will be as a primitive Fifo, and that's okay. Well, that's a very dangerous case actually. If all the Arbits are, all the Arbits are 1, that's probably everybody is using. People are using these pages. Probably I'm going to trash, and we'll talk about what trashing is. Good. Okay, so this is the second chance algorithm. If A has Arbit 1, I would put it at the beginning again, clear the Arbit, and it goes that way. Okay, so second chance Fifo. Loaded pages are ordered in a Fifo list, all this again. And so this is the algorithm. Am I missing everything? I think I told you everything. Clear the Arbit, move the, okay. So for the worst case, your question, all the reference bits one, this one will turn into a pure FIFO. Okay, so people like this one, but this is kind of, I mean, this kind of maybe costly. I mean, cutting this link and putting this at the beginning of the linked list. Why don't we use a separate data structure like a circular linked list? So I'm going to do this. Make a circular linked list. Everybody is connected to everybody like that. Okay. So there is no beginning or end in terms of where is the end and where is the beginning. Of course, there is an end in terms of who is the oldest, who is the youngest, and etc. Okay, so what am I gonna do? I have this clock algorithm. Clock algorithm is very similar to, it is almost the same as the second chance FIFO. It says that, okay, I will keep a linked list of pages, but it's a circular linked list. Instead of cutting a node from the end of the linked list to the beginning, etc. No, I am not going to do that, but I will keep a pointer to the current node, current page. Okay, so it's like this, but I am going to keep a pointer like this. It will point to this one or that one or that one or that one. So it becomes like a clock. Okay, so my pages, page numbers, okay, and if they are being modified or referenced, etc., etc. So basically we are running the same algorithm. If I am going to, if I need a page, if I need a new page and need to replace something, I look at this next frame pointer. If next frame pointer points a page, okay, that is not in use, that is not referenced lately, okay, then I am going to replace it. Otherwise, I will move this hand from this location to this location and make this 0. Okay, now I'm going to check it. If page 191 recently used, the answer is yes, it's somebody's used. So I am going to make it 0 and I'm going to advance the page. Now I am looking at this one, okay, page 556, nobody used it recently, so I am going to replace this one. Okay, and again move my hand like that. So I am not moving my page nodes anywhere from the beginning of the from the end of the linked list to the beginning of the linked list. Instead, I keep this pointer. Okay, so that pointer is simply a number, right? I mean, at the beginning it was 2, now 3, now 4, now 5, just an integer. Okay, so I keep advancing that pointer to show me the current frame. And when I load a new page, of course I am loading it in here, right? In this place. Okay, so exactly the second chance algorithm, second chance FIFO algorithm, but a little bit simpler data structure, more efficient. Okay, each page has a reference bit, and a page is referenced. I know that its Arbit is 1. I'm going to clear it and move it out. Okay. So each subsequent reference to this page again sets bit to 1, and I know that bit is set. Okay, so that's the clock algorithm. Okay, so the clock policy is, okay, finding a page to replace, the next frame pointer. I keep advancing that pointer from frame to frame. And as long as the next frame pointer encounters a page that is with a reference bit of 1, I keep resetting it and moving the counter. Okay, and eventually, if all of them has the Arbit 1, that pointer will come back to the original frame. Then I will replace it. Good. Any questions? Okay, good. So as you see, these algorithms are, of course, they are talking about, these algorithms, they will talk about replacing a page, and these are all privileged operations. As a regular user, I shouldn't be doing this kind of a thing. It's an operating system task. But making a decision which page to replace doesn't have to be done in the privileged mode. I can run this algorithm in a special user mode process, okay? That special user mode process, of course, it cannot change the page table, because I need to change the page table in MMU, right, after doing this, after loading and everything. I cannot change the page table, I cannot modify the page table, but as a regular program, as a regular process, I can tell the operating system which page to replace, okay? So I can run this main algorithm as a regular user program, and the kernel will ask me to do this, and I will do my computation, and I will tell the computer which page to replace. That means what? Why am I doing this? I am doing this because I like to keep my kernel small. Okay? I like to keep my kernel small. My kernel only modifies the MMU tables. My kernel only does the page replacement. The main algorithm is run in the user mode. Okay? So if something happens with my user mode operations, okay, that error will not affect the kernel much. That's the idea. Okay, that's why we say that keep the mechanism and the policy separate. Mechanism is just the making a modification in the page table. Policy is making a decision which page to replace. So this clock algorithm can be implemented in user space in a special process. By special process, I mean just another process, but operating system owns that process. Okay, and it tells the operating system this page is going to be replaced. Okay, and that the policy is here. Okay, finding the page to replace. Good. Okay. So let's keep. Okay, this is a good algorithm actually. This clock algorithm. It's a good algorithm, but I mean, all the not recently used the Fifo or the clock algorithm or the second chance, we actually, I mean, look at this Arbit only, and Arbit says that, okay, somebody has recently modified me. It doesn't tell me at what time. Okay, if all of them are Arbit 1, I replace the oldest one. But oldest R1 doesn't mean that that page is not being used. Okay, maybe some other process, maybe some other page has has to be replaced, but I am replacing the oldest one if all the Arbits are 1. That's why we don't like this property of the clock algorithms. Then they have invented this least recently used algorithm. Okay, least recently used algorithm is not recently used. Okay, least recently used. So it kind of tells you that you are going to measure how recently this page is used. Okay, how recently this page is used, and we are going to look at it. And for this, if we have the hardware hub, that would have been perfect. And that's what we're going to look at. If we have the hardware hub with the least recently used, okay, hardware assisted recently used, but then we are going to say that this is too expensive. Not all hardware can support this kind of addition to the CPU, to the MMU. Maybe we can emulate the same thing with software, but emulation will not be exactly the same thing. So it will be approximate LRU, but it's going to be a good algorithm. But before that, let me take some break, 15 minutes. After the break, we will continue. So let's be here around 11:32. Hayır imzalayamaz. Hayır. Zamanında gelin arkadaşlar yani. Sınıfın yarısı boşluk başladığında.
Hafta sonu bir daha verilen bir şey
Tamam, hemen
İkisinden analizinin son günü bu şekilde direkt çözüyorlar. Şey olacak. Şu anda önceliğin çevreleri. O ikinci yaptığımız tamamlayayım. Analizini yapıp direkt %50 olsun. Kalan süren yaklaşık bir gün. Üçüncü tanesine bakalım.
Ya bunlar şey kısa işte.
Bilmiyorum ama öyle söylüyor. Eğer süren bir günde varsa muhtemelen gelişme yarım kalmasını çünkü analizini yapmadan boş yapacak. Öyle mi? Son, bir sonraki soruya kalacak süreye bağlı. O dördüncü soru evet. O bir önceki bonus kısmındaydı. Bonuslara bakamadım ya. O ara başka bir şey daha vardı. Bonuslara bakamadım ya. Galiba projeden dolayı. Başka bir şey var. Sadece o 4 soruyu yaptım. 4 soru vardı o bonusda. 2 de bonus vardı. Bu bonustaydı. Çünkü önceki bonuslara bakamadım. Yetim vardı ama yetişmedi. Hiçbir zaman bırakamadım. Şimdi çıkalım aslında onları da bir şey olmayınca şöyle yapmadım. Ödevlerimiz bir şey yok. Çünkü o hızlı işlerinde diyor. Şu an bir dakika 6'yı verdi yani. 5'inciye birinci yok. 3-4 fena değil.
Daha az şey yapıyor, daha az operasyon.
3-4'ten bir tanesi ilgili referans olduğu için o da yarım. Diğerleri fena değil. Bundan sonrakileri de benzer performansı
O var yani başka. Bir de şey var. Bir tane soru vardı ya. Running waiting.
bugün mesela
Blok vardı ya. O şey. Onların hangisi olmaz.
şeyden dolayı kötü var. Ben geri kaldım.
Bir tane olmaz var.
Yapamıyorlar.
Ama derslerden karıştırıyorlar.
Korumuş bir borçlar var.
Şeyden mi?
Onun boşluğunda da var. Bir dersinden bitmeyemedim.
Bloktan rengi yok değil mi? Tamam.
Yani dün bir dersi akşam izledim de.
Rating'den
Yok yani.
bloktan rengi.
Kaydını indirdim ama.
Video var.
Ama yok yani.
Birden bloka da var.
İzlesem de anlayacak şeyleri değilim. Hani sadece yani şunlara değinmiş. Gün derse girelim. Anlarım anlamam. En azından kayıt olursa fazla.
Ben o
Bizim
sana
belki
söyleyeyim.
Doğru işin altına
Ben
bir sonraki dersi yarın. Çarşamba günü akşam
Waiting'den
sonraki
ya
yükler düştü ya.
da bloklar rengi. İkisinden
Benim o yapmak durumunda bunu kullandım. Tamam, Perşembe günüydü. Aksi takdirde çarşamba günü izlerim.
Ya öyle de.
Ben nasıl yapayım? Sen biraz tiyatroya alamazsınız düşünün. Evde şeklinde siz bakmıyorsunuz. Tam yerden çıktıktan sonra bir şey yapmayınca ooo. Ben açık sözüm. Çalışıyorum, çalışmıyorum. Açık söylüyorum. Çalışıyorum, ne olmaz sürekli.
İstediler verdi. Allah'ım çok kötü.
Neydi bu şey adı? Slack.
Çünkü geçen
Slack'ten sporda geçtik.
Ama bir de uçurdu mu ya?
Şey yapıyor. 10.000 mesajdan sonra
Sabah.
siliyor. 10.000
Geliyorum,
mesajdan
geliyorum. Biraz
yani
evden
sadece 10.000
geliyorum. Ama
mesaj
çıktığıma göre 5 dakika falan
sadece
geçti.
10.000 mesaj tutuyor. 10.000 mesajdan sonrasında silmeye başlıyor yukarıda. 10.000 mesaj fazla değil işte. Mesela diyelim başka biri girdi mesela. Tamam mı? Ya buraya girdi mesela. Adam önceki mesajlara bakmayınca 10.000 tanesine bakabilir sadece. Yani mesela bir sorun oluştu. Bir sorun oluştu mesela yukarıdan silmeye başlıyor. Yani şey otomatik siliyor. Yani Discord sınırsız mesela. Bir de burada bilmiyorum. Çok belli. Ama buranın J'yle entegrasyonu var mesela. O çok güzel. Her yer yani entegrasyonu var. O çok güzel. Eskiden şey çok iyi, UI falan çok güzelleştirmişler de yine üstte tutmuyor yani şey ifade etmiyor. Ne Slack mi? Şey işte benim çalıştığım yere girdiğim zaman Slack kullanıyordum. Ondan sonra işte dediler ki bu disket deneyelim. Çünkü orada hem sesli, görüntülü bir konuşma vesaire serverler vesaire daha iyi falan. Ondan sonra oraya geçtik. Bak ne kadar oldu biz geçeli? Bir ay falan oldu işte daha. Ondan önce Slack kullanıyordum.
İzlemedim hala.
Slack okey de.
İzlemedim sen. Sınava çıkmıştı çok güzeldi. Kostlara falan aday oldu.
Evet.
Burada hadıl var mesela.
Aha.
Burada ikili, üçlü, dörtlü, direkt hadıl sohbet odası var.
Yoklama ver.
Şey ona bastığın zaman sen mi odayı oluşturuyorsun?
Yok.
Aynı şey
olmaz mı?
Olayı ben oluşmuş oluyorum. Giriyor ama mesela şöyle bir şey var. Sen gidip API stand-up'ın hadıl açarsan, atıp API stand-up'ın hadıl açıyorsun. API stand-up'ın.
Öğleden sonra kalacak mı?
Yani şunu şu API stand-up'ın
Kendime tatil arası.
Yani burada şey açıyorsun. Sesli konuşma açıyorsun.
Sesli konuşma. Ben buradayım. Sesli bekliyorum.
İşte Discord'da şey var. Sesli konuşma hala da var. Tamam mı?
Discord'da mı ya? Daha şey de var. Burada bilmiyorum.
Ben olsam gelmeyiz.
Öyle bir şey varmış. Bana öyle söylediler.
Database'e bak.
Ben de söylenildiği kadar
Bir
biliyorum.
tane
Benim
geldi.
bilgileri falan
Geldi.
nerede
Biri de.
sorarım?
Bilgisayarda ben içine
Bakayım mı?
hem online yaptım.
Acaba
Hem de
mesela şey
yapmak
diyebilir
için.
mi? İstediğiniz yerden alabilirsiniz.
En o sese gıcık bir durum vardı gerçekten. Şey aklıma hemen şey geliyor.
Belki o kalmıştır bu arada.
Members can send unlimited messages in Slack Bak onun most recent
Adam şey dedi ya,
canvas söyle and be in your workspace.
yani 14 hafta.
Sadece 11 tanesi görüntülenebiliyor. Net buluyor galiba ama sadece 11 tanesi görüntülenebiliyor.
Bence 11 yapalım. 11'se de
Keep in mind that you will only be able to see
ben
messages
şimdi
in
onlarla galiba
public
hepsine
channels, private channels,
hepsine girsek 3 hafta gelmem. Hesaplarız yavaş.
10.000'den gerisini o zaman öyle düşünüyorsun.
yüksek
Sen
ihtimal.
kayıtları.
Ya yüksek ya özellikle yapacağım ya da bilmiyorum onlar direkt
Böyle
izlemişler.
şu ana kadar da
Normal üstünde
yani hangisi ödev veriyor, 5 gün veriyor mesela, 6 gün. Ben 5 gün şey izliyorum.
Hayır, bak şöyle düşün.
Sonra bir
Sorunların olduğu bir
daha izledim.
kanal düşün
Bu
mesela.
akşam
Bütün problemlerin olduğu bir kanal düşün.
en geç yani.
Diyelim, hayır, aynı sorun gerçekleşti ama çok önce gerçekleşmişti. Tekrar aynı sorun tekrar yaşanmak gerekiyor. Discord'da CTRL'de hemen arıyor, buluyor. Böyle bir sıkıntısı var. Diğer türlü iyi zaten.
3 saatte bitirir.
Bir de şey böyle, profesyonel biraz daha.
Benim de
Slack biraz daha
ben telefonu uzaklaştıracağım
Şirada
artık. Yani geçen
tas kazandığında buraya geliyor falan. Bayağı iyi yani.
şarj
ya bir de aynen bir de şey
telefon zaten bağlanıyor.
Tabii ki
Bilgisayar
entegrasyon.
deniyor.
Şirada onlar hepsi beraber entegre
aynen
oluyor.
yani mesela Öcü aslında GitHub üçünü böyle
Telefonu hep aklıma Türksel ya. Türksel reddetti.
Siz ne kullanıyorsunuz?
kanka Öcü
Değil mi? Ya ben sana hatırlamıyorum. Galiba şey oldu ya, bir tane uygulamada böyle dandik bir şey yolladı test gibi. Ben geçen sene o yaptığım şey onu yolladı direkt benden. Yani geçen seneki yaptığım şey yolladı. Direkt uygulamaya girince.
yani
Ya, işte yaptırmadım. Direkt aynısını yolladım. Herhalde o yüzden böyle. Çünkü geçen sene de reddetmiş. Ben niye aynı şey yaptım? Geçen sene niye reddetmişsin? Yo, direkt reddetmişsin söylemişler ya. Hatırlamıyorum ki spamlara düşmüş. İstemiyorum ya. Ama bayağı başvurmuş. Son sıraladığım birkaç şey var. Kötü baktım. Sınav yolunda. 1,5 saat İngilizce sınavı mı olur abi? Böyle benim de beyin kitapçılık vardı. İyi sayılır mı? Bence de hiç fena değil yani. Ne yapmışlar? enerji, onların. Ben de Nuri'den başlayarak deneyeceğim. Sınavlar, işler benim sınavı. Evet, iki sınavım var. Database ve Human Computer var. Biri sabah bir haftaya bu saatte sınav oldu. Ondan önceki gün de muhtemelen geldi. Ancak çünkü bitmez. Cumartesi ilk sınav. Özellikle Allocation. Kaydolmuştu ya. O da bu haftaya denk geldi. Harika.
Bir server değil, iki server. Şöyle bir şey, yani client'tan server'a gidiyorsun. Server birisi, ikinci server'a gidiyor. Evet, onu private ayarlıyorsun. Edemezsin. Onu şeye atacak, öbürüne atacak. O da bir server'ını atacak. Bitirme var.
Aynı şey yazınca soru zaten şey oluyor. Kelime oluyor.
Herkes soruyor. Direkt soruyorlar. Oluyordur ya. Sonuçta şey yapabiliyorsun. Sayfa videomuza yazıyoruz karşılığı. Sırası yok. Mesela
Okay, so let's look at this new algorithm, LRU. Okay, LRU says that a page that hasn't been used recently is unlikely to be used soon. Well, it is similar to what an RU says, not recently used. Okay, but this recently used will measure the duration, the exact duration. At least if we try to measure the exact duration, this page has not been used. Okay, so how can we implement this? We will ask help from the hardware. Okay, so remember our MMU unit inside our CPU. Okay, there is an MMU, and MMU is connected to our memory like that. Okay, this is our memory. So every time I produce a virtual address, this virtual address is translated into a physical address by this MMU, right? So every time I make a memory reference, this MMU comes into play, and it makes this translation for me, and it produces this physical address. Okay, so why don't we modify our MMU in a way that it keeps a 64-bit instruction counter. Okay, so inside the MMU there is a counter, 64-bit counter. Okay, this is a counter. That's one addition. On each memory reference, I store the counter in my page table. Okay, so if I am making a new reference, a memory reference, I will look up from the page table. This is my page table, right? So I will look this up from this page table, and using the offset and the page table replacement, I will produce the result, and I will produce the physical address. But while I am doing this, with this memory reference, I store the counter in the page table, and saying that I access this page at this counter time. Okay, so I know exactly the last time that page has been accessed. When the page fault occurs, okay, I scan my page and I found the lowest value. I say that, okay, I access this page at this time, and this is the actually the least recent used page. Okay, so I know exactly which one is least recent used. Okay, it's not like in NRU. Remember, in NRU we have the classes. If I have a class of 0, 0, okay, I can replace any of them inside randomly. I pick just one of them. Okay, this is not doing it that way. This one knows exactly at what time each page is referenced or modified, because I have this special feature, hardware assisted LRU. I have this special feature. I have a counter. That counter is incremented at every instruction. Instruction number 1. Okay. Whenever I execute an instruction, I increment this instruction counter. And whenever I make a memory reference, I put this counter to the reference page. Okay, so that kind of solves the whole problem, and it works beautifully. Hardware assisted LRU, but the downside is, of course, I need hardware support for this. And the nice thing is, since it is supported by hardware, okay, it is done automatically. I don't need to do much about the incrementation of the counter and updating the page table and etc. Okay, so this is all done by the hardware. That's nice, but again, I need the hardware help. So if I don't do hardware help, then I am going to do the same thing with the software. Let's look at the software simulated LRU. The first thing is first, I can't do the same thing in software. That would be too expensive, because this one, incrementation of this counter and modification of the page table for each memory access can be done in hardware. But if I try to do the same thing in software, then that will make my memory access times maybe 4 or 5 times slower, right? That's not going to be good. Okay, so that's not acceptable. So I have to find a compromise. So I am looking at the software simulated LRU. Again, we have an array of counters, one per page. Each page has a counter in it, like the LRU, hardware assisted LRU. Each page has a counter in it. That's one thing. Okay, and this time I am doing this processing at every clock tick, not every memory reference, but every clock tick. At each clock tick, add the value of R to the counter. So something like that. So this is my page table. I have a counter at the beginning. These are my R and M bits, okay, and these are my counters. At the beginning, my counters are 0, okay. When the clock tick happens every 50 milliseconds, I check these Arbits, okay, and I add these R values to this counter. So this counter becomes now 1. This one is 1. This one, they are all 1. Okay, and then after that, I clear all these ones. They are all zeros now. After the clock interrupt, and my program is running, and when the clock interrupt happens, I am checking all of my Arbits again. Let's say this is 1, and this is 1, and this is 1 now. And I do the same thing. Add these values to the counters. Didn't change. This one became 2, and this one became 2 again. This one became 2. Okay, and change them back to zeros. And do it that way. So I am kind of calculating how many times this page has been accessed. Okay. The thing is that these numbers get larger and larger and larger. So small number and large number doesn't mean much to me, because large number doesn't mean that it is accessed recently. Maybe it has been accessed so frequently some time ago, but it is not being accessed at all. Okay? So this is a little bit different than this approach. This one always stores the current instruction number to the page table by the hardware. This one tries to do the same thing, but not at every memory access, but at every clock tick. And I keep adding these numbers, and these numbers gets larger and larger and larger, and the problem is it never forgets. Okay, it just kind of measures how frequently. Okay, it kind of measures how many times I use this page. It doesn't tell me about what happened recently. Okay, so that's not a good idea, but we can do this nice solution. Okay, NFU with, okay, not frequently used with aging. Okay, instead of adding the value to the current counter, we do this: shift each counter to the right. Shifting a counter to the right means that, you know, what does that mean? It means dividing it by 2, right? Shift the counter to the right, and I add the arbit to the high order bit, the most significant bit. Okay? If let's say, this is my table again. This is arbit, mbit, and the other stuff, and this is my counter. In my counter, let's say I am doing it in a binary format, 0 1 1 0 1. Okay, and my arbit is 1. So what I'm doing is that I'm going to shift this counter to the right, so it will be 0 0 1 1 0, and clear the arbit, but put this arbit to this location. So my new value will be 1 0 1 1 1. Right? Is that no, 1 1 0, sorry. Okay, so I am not just simply adding the value to the numbers arithmetically. I am making this bit the most significant bit of this counter. So the most recently used counters, okay, most recently used counters will have the highest values. Okay, so the recent references have more weight. So this is called not frequently used with aging. Okay, so this was just not frequently used. Okay, this one just measures how many times it is used. Okay, how frequent it is used. That's not good, measuring how recently it was used. But this one, not frequently used with aging, does exactly that. Okay, how many times it is used, but it is mostly affected from the recent uses. Okay, instead of trivial adding it, I shift right and add it to the beginning of the most significant bit of the counter. Yes.
I don't understand how LRU is forgets the other.
LRU does not. I mean, the hardware assisted LRU.
Yeah.
This one doesn't forget. It just says that. Okay. This says that. Okay. This page access the memory at time 1. This page access the memory at time 2. This one 7. This one 8. Okay. So whenever a page fault occurs, I scan this table, and I say that, okay, this page did not access the memory. Did not access the memory recently. Okay, this is the least recent use of the memory. Okay, there is no aging because I am keeping the actual access times of each page by the help of the hardware.
Why there is a problem with NRU in that case?
There is no problem with LRU. The problem with LRU is it needs hardware access.
NRU, not recently.
You mean the not frequently used?
Not frequently used, yes, sorry.
Okay. So NFU is, okay, NFU is this. I keep What is the original NFU? NFU says that at every clock tick, add the value of R to the counter. So just check the page R and keep adding this number to the counter. This doesn't give you any information about the recent use of that page. This just will give you how many times I accessed that page. Okay? After I loaded that page into my memory, this will measure the number of times that you have accessed that page. It doesn't tell you about how recent you have accessed it. Okay? Maybe at the beginning you have accessed this page a number of times, but recently maybe you are not using it at all. Okay? So this will never forget. I mean, you will get numbers like, for example, this one 100 times accessed, 207 times accessed, okay, 20 times accessed, 21, and this one is 1. So which one would you pick in here in this case? Of course I would pick 1 because it was not accessed much. But maybe that 1 is coming from the last interrupt, right? Maybe it is the most recently accessed page out of all of these. Maybe this 207, it was accessed long time ago. I don't know. Okay? So that's why NFU, we don't like it. It doesn't talk about the time. It talks about how frequent we are accessing a page. Okay? So that's NFU. So we added this feature to NFU, not frequently used with aging. I shift the bits to the right. I divide the counter by 2, and I make this one to the most significant bit of it. So there is an example here. Let's say for each page I have total of 6 pages, and these are the counters for the pages. Okay, so previously, okay, so this is what happens. At the beginning all the counters are 0. Clock interrupt happened. I checked the Arbits of each page. So there are total of 6 bits. So basically, since everything was 0 at the beginning, I shifted right, nothing has changed. So I put this one here, right? I put this one here, this one here, and this one here. Okay? So this is the case now. Next time the clock interrupt happened, I am shifting all these numbers to the right. See, this one is again shifted to the right, but this time 1 is here. Okay, so this part is the same as this part. Shift right and add this one at the beginning. Again, do the same thing with this. I am shifting it to the right, but this time it is 0. 0 comes here. Okay, so when I look at this picture here, which one is the least recently used? When I look at this one, well, 0, 0, 0, 0, it was never used at all, right? I would replace this one. And I think the largest number is 1, 1 and 1, 1. These two are the most active pages. Maybe I should not replace these 2 pages. These numbers are very high. Okay, and I should replace this one. After that, maybe I should replace one of these, but not this one. So look at the difference between these two. These two have been accessed just once. Okay, but this one is the most recently used one out of these two. Okay, so this is how frequent I am. Okay, number of ones inside these numbers will tell you how many times these pages were accessed. Okay, number of ones, but the order makes it a binary number, and that binary number, the magnitude of that binary number will tell you not frequently used with aging value. Yes.
When smallest ones are equal, 2 or more smallest.
Yeah, just pick a random one.
Random.
Yeah, sure. Okay. Good. Well, I mean, if you continue that way, let's look at the last one. At the last one, I have this picture. So it looks like I would replace. Which one would you replace? It looks like this is the smallest one. Is that the smallest one? Yeah. This is the smallest one, right? So let's look at this one. This one has been accessed only once in its lifetime, but it was accessed fairly new, like 3 clock cycles ago. But after that, all the other pages they have, I mean, these are kind of, you can see that these are the bits that shows me the who is accessed in the last clock interrupt, and these are the bits 1 clock interrupt before, and these are the bits that are 2 clock interrupts before, right? It goes that way. And would you say, I mean, isn't this expensive? I mean, how can I keep such a counter for each page frame and update that? Well, this is expensive, but this is not, I am not doing this at every memory access, right? I am doing this only during the clock interrupts. Okay? I am doing this only during the clock interrupts. Where is my, yeah. At each clock tip, okay, add the value of R to the counter after shifting and by adding to the most significant digit. So remember the tools that operating system made available to us for our page replacement algorithms. This time I am using the clock interrupts for this purpose. I am using the clock interrupts heavily. Okay? Good, so this is simulating LRU in software, and it's called NFU with aging. Okay? NFU with aging. Okay, any questions? Okay, if there are no questions, I am going to do this. I am going to well, I think I will have to talk about this working set thing, but maybe I should I talk about working set clock? Okay, well, clock algorithm will come back again, and I wondered if I can talk about it now, but no, I will not. Okay, so let's look at this one. Frame allocation to processes. Okay, we usually follow this policy of demand paging. Demand paging is this: never allocate any frames before they are used. Okay, once a process starts running, okay, load only the first page that the first instruction belongs to. Okay, and run that instruction. If it needs extra pages, then you load them. This is called demand paging. You don't load any pages in advance by anticipating that I will need these pages anyway, etc. So demand paging will allocate frames as necessary. Okay, and usually we keep maybe 20% of our memory available. It is in free, so we don't wait until our memory is filled up. We like to keep 20% of our memory always free, so that when a new application starts running, or when a new application needs new frames, those frames are available exactly. I don't have to do any page replacement. Page replacements are usually done to make that 10% or 15%, 20% free list available during the idle times of the operating system. So when you look at your task manager, either Windows or the Linux operating system, you will see that although you have many programs loaded, okay, so your memory will be around 80% full. Okay, that doesn't mean that all the total memory required by all of my processes are just add up to 80% of my memory. No, I mean, if I add up all the total of the memory required by my processes, it would be maybe 10 times more memory than my physical memory. No, that's not it. The thing is that I like to keep many pages available for applications so that they can run very, very fast. Whenever they need a new page, that page is available. I don't have to deal with this page replacement algorithms while the program is needing those valuable memory. Okay, so that's how the things are done. Okay, see, when I started talking about this, my memory was like 80% full. Now it is 70% full. Right? I didn't terminate any programs. I didn't do anything different. I just launched this program and I just looked at it. Okay, so what did it do? It just replaced some of the pages. It said that I am going to write these pages back to the disk. I will make these pages available. Let me try to load, for example, let me try to do, see, it just increased. Let me try to see if I can, yeah, let me launch this Explorer. I am launching it. It is trying to load something, so my memory is increasing and increasing. Okay, let me do this. Okay, so it is 80% now. If I wait a little bit, see, it is going down. So it is 73%. If I wait a little bit more, maybe it will go down to again 68% too. Okay, so what's happening when this program needs pages? So I think it needs. Let me try to load a new page now. Yeah, can I? Maybe. Good. Okay, I'm loading a new page. If I can. No. Yeah. Oh, because I am not connected to the internet. That's why it is not doing anything. Okay. So the thing is that it makes some part of the memory available all the time. Okay. And doing that is not easy. How do I do that? It just scans the occupied pages, and by looking at whatever the page replacement algorithm is, it tries some of the pages back to the disk if they are not used, so my free list is always available. That's called the demand paging. Okay, and we usually try to run this page replacements during the times where the system is idle, mostly. Okay, and the trashing is this. I can't do this anymore. Okay, my computer has many processes running at the same time, and I am really running them at the same time. I mean, it looks like I am running many programs at the same time in this computer, but usually I am writing out either this drawboard program or the Chrome browser or the other one. So one of them is really actually intensely using the CPU. But in cases where I am running many programs at the same time, like I am running this OBS recorder and Teams video broadcaster and this viewing program and etc., I am actively running them, then they will all need memory at the same time. So they will all say that I need this page, but the operating system wouldn't find any pages to replace to the disk. So it's going to replace a page that is actively being used. Okay, so I am replacing a page. I know that will be loaded back from the disk in a few moments. So I keep loading it and writing it back to the disk. It's called trashing, and trashing is expensive. Trashing is bad. Trashing is a bad thing. Trashing is Trashing is a bad thing. Is a bad thing. Okay, it's not good. And once trashing starts happening, then your operating system doing replacing pages back and forth between disk and the main memory. Instead of doing useful work, we are doing this unuseful, I mean for me, unuseful work of writing stuff to the disk and loading back. And that's not going to be good, because as an end user, I will lose my interactivity. My expectations of when I click something it should happen will not be met, and that will be bad. So the main reason for trashing is running too many programs. How do you solve the trashing problems? Okay, don't run too many programs at the same time, or buy some extra memory. Okay, add some memory to your system. I mean, if you have to use 5 programs at the same time actively, they are all trying to use the CPU all the time, then there is no solution. Either you terminate one of the programs, 2 of the programs, or you buy some extra memory. Okay, so trashing is something bad. Okay, so this idea of trashing and the idea of each process needs some certain memory to run. I mean, if Explorer, the total size of Explorer is, let's say, 20 gigabytes, I never load 20 gigabytes of memory. I never load 20 megabytes or 20 gigabytes of data to my memory, because I don't have that kind of memory. This Explorer doesn't use 20 gigabytes of memory all the time. It uses only a small part of it, maybe 1 gigabyte of it. And when you see it, okay, when I load this up, it looks like, in this case, okay, this guy is, okay, let me do it, okay. The program Teams is using 500 megabytes at this time. Draw board is using 350 megabytes, okay. Compared to their sizes, process sizes, these are very small numbers. These are only the pages that are being used, okay. These are only the pages that are being used. So if I know how many pages Teams will need, how many pages draw board will need, how many pages this OBS Studio will need, then I could use that information. To see if I run into any trashing issue, okay? Because I cannot go lower than those numbers, okay? If I add the minimum required memory for each of these processes, if I add them up, if they are larger than my main memory, then I will trash, right? So let's try to see how we can approximate that measurement. We are going to call it working set, okay? Working set is this, okay? At any time, as we see, my draw board is using 350 megabytes of memory space, although the process size is maybe a few gigabytes. So it is using only 1/10 of the largest process size that can be for the draw board, okay? So my draw board program is using only fraction of it, okay? And we call this fraction the working set, okay? I need this set of pages. That's my working set at this time. And by starting from this idea, I write this special function, working set function, WKT. At time t, okay, working set W is the most recent reference pages for the last K references. For the last 100 references, how many pages did I use at time t? Okay, that's the idea. For the last 100 references, K is 100 in this case, okay, how many pages did I use? Okay, I am expecting this to be a number, but that number is not as large as the whole process size. Of course, if you make this K very, very large, like 1 million, for the last 1 million, 1 billion references, how many pages did I use? that will turn out to be your whole process size. But I am not interested in the whole process size. I am interested in only limited number of references. Okay. And here is one example working set for a program. This limit here is see, it is asymptotically trying to approach to this limit. That's the process size. This process will not use more pages than this process size. But I don't keep my whole process in the memory because I don't use many of these pages. If k is just 1, for the last reference, how many pages did I need? Of course, just 1. Okay. For k is 1, whatever t is, it is just 1. Okay. When k's get larger, of course, this number will get larger, and this is monotonically increasing function, working set function. Okay. And if you keep this k large enough, it will approximate the process size. Okay. So the thing is that for certain numbers of k, this is what I am interested in. Okay. So for certain numbers of k, let's say 1,000, 2,000 references, if I keep that working set number of pages in my memory, this process should be happy. It should run. Okay. And if I add up all the working set requirements of all the processes, and if that number is smaller than my total available memory size, then I have a happy operating system, happy working environment. Otherwise, if these numbers are adding up to be larger than or very close to my total memory size, then I will be trashing, and trashing is not a good thing, as we said before. Okay, so why am I telling you all this? Because we are going to write our new page replacement algorithm using this idea. Okay, we are not going to replace the pages by looking at how least frequently they are used. We are going to replace them by looking at our working set size. Okay, if that page is in my working set, then I will keep it. Otherwise, I will replace it. That's what we are going to do. That's the working set algorithm. Did I miss anything? Yeah, we talked about it. Yeah, W is monotonically increasing. It has to monotonically increase with respect to k, right? So when you increase k, the excesses, number of excesses, of course, you have to approximate this number of process size. We talked about that. Okay. If there isn't enough memory to hold the entire working set, then the program will crash. And the trashing can happen. In fact, the trashing can happen even with a single program if the memory requirement of that program is very large. For some scientific calculation software, like or the design software, like for example, some versions of MATLAB, some versions of AutoCAD, and etc. They need lots of space, memory space. And if you don't provide that memory space, within the same program, actually, you will start trashing. Okay, I have a single process on my computer, and still it is trashing because that program needs lots of memory. Okay, good. Okay, so let's use this working set idea. Okay. Before running a process, make sure that the working set is in the memory, and with some value of k. But so, what value of k should I choose? I don't know the answer. The value of k, I don't know. But I mean, you cannot make a very big mistake by choosing the k, because I mean, this is monotonically increasing function. The function is not like this. If I had a function like that, okay, choosing this k over this k has some consequences, because their values are very, very different. By moving to the left or to the right a little bit, your working set size changes a lot. This will not happen in this case. Why? Because this is a monotonically increasing function. By choosing a little bit different k will not make your results a lot different. Okay, so because W is asymptotic, exact choice of k isn't critical, as long as it is large enough, as long as it includes all the things. Okay, so the trick is to determine the working set. Okay, can I keep all that working set within this k in my memory? Okay, so we are going to, again, we cannot measure the exact working set, we are going to approximate it. Okay, ideally we would track the last memory references. Maybe we can use this software simulated LRU or aging NFU. Okay, ideally we would track the last memory references. That's too expensive. Instead we track the pages reference during the last seconds, like the NFU with aging. For each page we are going to keep a virtual clock field like we did before. At each clock tick we update the clock field in R, and pages not referenced during the last seconds will be discarded. So actually, I mean, what did I do? Well, this looks like very much like the NFU with aging. Yeah, it is very similar. I have a slight difference, and you are going to see it in the code that I'm going to show you. Okay, so current virtual time, and this current virtual time is like it's not an instruction counter, because keeping an instruction counter is expensive. It needs hardware help. This virtual time kind of counts the number of clock ticks. Every time a clock interrupt happens, I increment this virtual clock time. Okay, so whenever the clock interrupt happens, I increment this current virtual time, and I scan this page table. For each page table element, there is a virtual clock time field. Okay, if my Arbit is reference, it is 1, I update that value with this one. If it is not 1, then I don't update it. So I kind of keep this information. When was the last time this page was referenced? Very similar to LRU, least recently used with the hardware help, but this is not in terms of memory references. This is in terms of references of that page between the clock interrupts. Okay, that's the table. So when a page fault occurs, this is the algorithm. Okay, this is the algorithm. Oh, sorry, this is not the algorithm for the page fault occurs. This is algorithm when the clock interrupt happens. If R is 1, set the time of last used to current virtual time. So if this one, then I'm going to put this one in here, and this one, put it in here, not here, oh no, here too, not here, this and this and this. So I'm going to update all of those. If R is 0, if I did not reference that value, then I will calculate the age of that page. How do I calculate the age of that page? I will take the difference between this value and this value. That will give me the age. How many clock interrupts happened between this time and the time where this page has been accessed? Okay, if that age is larger than some threshold value, this is the k value, remember you should choose a k, then I should remove this page. If R is 0 and age is less than some value, okay, even though R is 0, I am not going to replacing it. Okay, or I'm going to remove it. So this one doesn't talk about the replacement actually. It says that don't keep any pages in the memory even though I don't need any page replacement. That's what it says. Okay? That's what it says. So it's like the picture that I showed you. Even though I'm not doing anything, my available memory keeps increasing, right? After a while, after I wait, because my working set for many programs are getting smaller and smaller. Okay, so that's the working set, the working set algorithm. It looks like, well, as always, this is the idea, but we are going to make this idea a little bit nicer. We are going to combine this idea with the clock idea, and I don't have much time maybe, but I will show you this and I will stop here. Next time I will pick up from this point. Working set clock algorithm. Okay, like the clock algorithm, we have a pointer that points to a page. Okay, and this algorithm works on all the pages on the page table, but in terms of which pages to remove, this clock algorithm will make that decision, but I don't have the time, but I'm not going to talk about it today. After that, I think I will be done with this page replacement algorithm. I just did not look at this one yet. After we look at this one, we will be done about these algorithms. And this is the last one that I'm going to show you. In fact, it is the most commonly used. Linux and Windows is using a variation of this algorithm. Okay, I guess that's it for today. Are there any questions? Okay, I'll see you on Monday then.